Hello, everyone. Welcome to our talk today. My name is Jelena Pjesivac-Grbovic. I'm a staff software engineer at Google and one of the technical leads on Cloud Dataflow product. Today, we're going to look at the data processing tools and their application and their performance, and how two cloud processing tools, Dataproc and Dataflow, achieve the excellent and optimal performance out of the box. So data processing performance, why do we care about it? Well, it matters because it affects the latency of our result. So to achieve our result, we have to spend time running the pipeline, and depending how efficient it is, it affects when our result is available. Depending on what your application is, the time it takes to get to the solution can be make it or break it event for your product. Another reason why the performance matters is the cost. Your applications run on the real hardware. Running on real hardware costs money, whether you use the cloud or you use the on-premise, right? So if it's inefficient, you're literally wasting money. So that's an important thing. And combining these two, it actually makes performance can make data analysis feasible or unfeasible. If it's too slow, we don't need it. If it's too expensive, we cannot afford it. So performance is really critical in making it possible for us to do a data analysis. So what are the factors that affect the performance? There are many of them. And first set of factors we're going to look at are related to your application. Essentially, the things that are sort of in your control. First thing is data shape and distribution. Are your old data records approximately the same size? Or they vary a lot, right? If you think of someone processing a social graph, a node that contains the social butterfly will be orders of magnitudes bigger than a node containing an average person, right? The other thing that's sort of similar but slightly different is the per-record computation cost distribution. Do all records cost the same? Like, does it take the same amount of CPU time to process each of your records? Or again, there is a big difference. If you think of something that's processing map tiles, like the processing a map tile on Antarctica versus processing a map tile in San Francisco, probably incurs different computation costs. And finally, within application space, the one factor is implementation efficiency, right? How well you were at optimizing it, how well you were at using the APIs that are given to you, how's your memory management, and things like that. So to address the application factors, there is a traditional performance tuning and optimization process, right? We profile our data, and we profile the application. Now, once we understand our data and application, we can perfectly split our data, partition it for execution in parallel, and we can perfectly schedule those tasks. Of course, this perfect, take with a grain of salt. But we can perfectly schedule the task, job will execute, and produce a result, and we'll be happy. If that was it, we're done, right? We've computed everything we needed. But in reality, this is not the end, right? We run our data processing pipelines regularly, sometimes even continually, right? So this process is a process that has to be repeated. And it sort of works, except expertise is required, right? Like, the person who can do the profiling in data and application is not easy to find, right? And the thing is, if you have one application, sure, you can maybe afford someone who will be, your expert and make it run great. But if you have hundreds, you really can't scale it. So what happens then is people copy tuning parameters from the one that was tuned. and then, and it keeps going, and you copy it, and you hope that it's going to achieve the same performance benefit it did for your original pipeline. But guess what? It usually doesn't. And especially over time, it gets worse. And you may not be even aware of it, right? So the other aspect of where the traditional performance tuning and optimization sort of break down is that it's not always possible. If you have a complex pipeline with multiple stages, you may not be able to reliably profile intermediate stages, because that data depends on actually data that came in, right? And if that changes, the properties of the intermediate data change. So you really can't always benefit from this. And finally, even if we did everything perfectly and we had a full knowledge, we are running on on the real system, on the machines that will have some things going on them, and they will not all behave the same. And that brings us to the execution environment as a factor of our data performance. So, big part of execution environment factors are workers. Some workers will be fast, some workers will be slow. Why? Who knows? There are many reasons why workers can be slow or faster. For example, most of the work nowadays runs in VMs that share the physical machine, and depending on the quality of isolation, one can affect the other, right? The other thing that is important is the networking. So network conditions are even less, you can even less isolate the networks in terms of the impact, and someone else using the same network you do will affect your performance, right? And finally, this is like resource contention, and this can be on any possible level. It can be resource contention in your code. It can be resource contention in a worker that you're running. It can be resource contention on a VM, or it can be resource contention on a service that you rely on. Imagine you're reading a service that can support certain amount of QPS, right? And then there is a big user that comes and pretty much uses up everything. Your job, all the jobs will slow down because of that, right? So the impact of uneven worker performance gets worse with scale. Amdahl's law tells us essentially that. And the more parallelism we have, the more serious bottleneck the serial part of our application become. Yeah. Okay. So how do we deal with execution environment? Well, I mean, you can remove slow machines, that's one, but that's not something you can do on demand and automatically. What people do is usually avoidance techniques. So things like a backup or worker resets. So if your application can detect that something is going slow, that a worker is slow, it can choose to use a different worker, or it can schedule the work done on that worker to someone else who is faster, right? And that's almost it, right? Like from the dealing with execution environment. Another factor that's related to execution environment factor in this is a system complexity. Your application uses an SDK, right? And when it runs, that SDK runs on some kind of a worker harness, right? A thing that takes your API calls and puts them in a system. And that runs in some kind of a container that runs on a virtual machine that may be running multiple containers, right? And that runs on a physical machine that may be running multiple virtual machines. And if you're doing distributed application, guess what? There are multiple physical machines, and they're connected by a network. So anywhere in this stack, something going wrong or something being slow affects everything above it, right? Okay. Yet we are not done with the factors that affect the performance. We have our dependencies, and I mentioned them, but we'll call them out here explicitly. So one set of dependencies is related to the client libraries you use. If you use inefficient implementation of something, it will affect performance of your application, right? And often client libraries we use are like I/O libraries, your connector to something. Convenience libraries like a parser or like a formatter. And then some domain-specific libraries, maybe some kind of a math library or something that you may need to actually compute what you need, right? System libraries are similar. Your VMs and all of this come with some predefined images, and they can have a good set of libraries or not so good set of libraries. Okay, so to summarize, the factors that affect application performance are, you've seen they can be static, like a system libraries or something, or dynamic, like the things that happen at the runtime, which were our worker and execution environment, for example. The data processing tools need to adapt to the application and the environment. And the underlying system and dependencies affect application performance, right? So with this, we'll look at the two specific Google Cloud processing tools, Dataflow and Dataproc, and how they tackle different aspects of the different factors that affect application performance. So first, we will look at the Cloud Dataflow and how it deals with application-specific dependencies and environment. And then we'll look at the Dataproc and how it deals with the system-level improvements. OK, so let's switch a gear and talk a little bit about the Cloud Dataflow. Cloud Dataflow is a fully managed, no-ops data processing. It offers unified batch and streaming processing power, and it uses open-source programming model using Apache Beam. It's designed to scale to millions of QPS if you're using it in a streaming mode, and also can run really large batch jobs. So how does the working with Dataflow looks like? You wake up and you write your Apache Beam pipeline. Then you take it and you submit it to Cloud Dataflow service. The Dataflow service in its behind has a bunch of backends that provide many different services, some of which we'll talk about, that are sitting there waiting for your jobs to come and schedule. So the service will schedule your job on one of these backends. This backend will take your Beam pipeline, run it through Graph Optimizer, do some annotations, some analysis on it, and it will come up with the initial configuration for your job, and will start resources for you on which you will execute that job. So it will start GCs, it will start, allocate the buckets and everything else that you may need for this job. Your job will start to run. You'll access your inputs. They can be on GCP or they can be external sources. We'll read them. You'll process, produce the output, and you're done. Okay? So this is our workflow. So what are the benefits of it, right? Well, it's fully managed and auto-configured. You don't have to worry about deploying your packages or jar files, pre-allocating VMs. You just submit your essentially job to the service, and it runs. And all the resources that your pipeline uses are allocated on demand. Okay? We also do automatic optimized execution graph. So we'll talk about that in a minute. We also mitigate the stragglers dynamically using something we call dynamic work rebalancing. And we can automatically scale at runtime to match the throughput your application needs. Okay? So if you look at these 4 benefits, 3 of them are trying to address the factors that affect the performance. So Apache Beam, looking at the optimizations, so pipeline graph versus execution graph. What Apache Beam gives you is a very intuitive programming model that allows you to express the complex computations simply. That's great, except that's really not the way you should be running this application. So once we have your pipeline, we run through many optimizations algorithms to provide the optimal execution graph that we can run that will produce the output that you want. So this also, like in this process, while we are optimizing, we try to estimate what is the initial configuration for your job that we think will run it well. And now, let's look at the dynamic factors and look at the stragglers. So what is the straggler? In this framework, the straggler is a task that takes longer than to complete than the average completion time across all the workers. So here is a graph, and I'll explain it. So first, on our x-axis, we have time. On y-axis, we have workers. This is a Gantt chart of the state of the workers at the given time. So each of the horizontal lines represents a worker and the tasks that were running on it at the given time, right? Like if you do the vertical cut. So what you can see that in this graph, the worker finished the shard, it start working on the next one, finish the task, start working on the next time, and things are going pretty smoothly. There is not huge variability between the end times. The execution with the stragglers looks different. Like some of the tasks are taking much longer than the others, right? And they're affecting our end time. Do these things happen in the production, in your real jobs? Oh yeah, they do. So this is a typical MapReduce-like pipeline where you have a read operation, you group it by key, and you write it. This is a job with 400 workers running for about 20 minutes. And if you look at what those 400 workers worked on, there are like these huge gaps where many workers sat idly while few other workers were trying to finish, right? And this is a big resource waste, right? So to address the issues of stragglers, we employ a technique called dynamic work rebalancing. So how does it work? So looking again on our graph with the straggler, we can see our completion time is, completion time of this job or stage will be once the red shard finishes, once the red task finishes, right? So what can we do? How can we address this? So first step in this is straggler detection. You first have to identify a problem so you can solve it, right? So what Dataflow does, it's on continually monitors amount of remaining work. So imagine we're on this gray line that shows our current time, and at that time we check what's the remaining work. This would be our completion time if we didn't do anything, right? So we run our algorithm to estimate how much work is remaining, and we come up with, this should be our average completion time. If everything was perfectly parallelizable, and we were able to utilize all 8 workers, this is when our job would finish, okay? So then, once we have this information, a worker can say, I'm behind, so what I can do is split. I can return a fraction of my work, so others can work on it, and I can finish what I have in a given time, right? And now we rebalance the work, and the situation looks better. It's not perfect, but we did save, some amount of time, and our new completion time is there. Clearly, there is more work to do. We should be able to parallelize this further, so guess what? We do. So we repeat this process over and over during the execution of the job, and your workers constantly get filled with the work. So what's the impact on a real job? This is, again, the same application we saw, like the 400 workers spending a lot of time waiting on others. And this is how this application looked like once we enabled this dynamic work rebalancing. So we say they're on 5 minutes out of 20, so a quarter. But this is a 5 minutes out of 400 workers, like 33 hours of CPU time. So it's not a small saving, right? OK. Now, we've seen how dynamic work rebalancing reduces straggler tail and keeps worker busy. But that's not the only thing we do. Autoscaling allows us to match the number of workers to the throughput your application needs. Okay? So it scales the number of workers automatically to ensure the pipeline is keeping up with the demand. It applies to both batch and streaming, but my example on this graph is streaming. So imagine your application is up and running, it has some kind of a QPS, and we run it with a certain number of machines. In this case, I think 12, and things are going fine. As the QPS increases, as you're getting more hits on your service, we will grow the number of workers to maintain the lag of processing low. And once the QPS rate comes down, we'll decrease the number of machines, because there is no need for them to be there. You can keep up with the traffic just with much fewer machines. Okay? So how does this how does the autoscaling play out in a bad job, for example? So we start the job. We do some initial analysis, like I said, during the optimization. And we come up with we should run this with the 3 workers. Okay? And things start running, and things look OK. But again, we're continually estimating when we will finish. And at some point, we have enough information to conclude that this is going to take much longer. We should really be working with 100 workers. So great, OK, bring up 100 workers. The beauty of GCP and easily scale up, right? However, the problem in this case is we don't have 100 pieces of work. We initially split it into 6 or 9, whatever, because we thought we needed 3 workers. And this is where the dynamic work rebalancing kicks in, right? Because now you have 100 workers, and you can generate work for them by using dynamic work rebalancing. And this is actually pretty cool. We call it auto-tuning, like many people call auto-tuning things. And you can scale up and scale down as needed. This is a job that started with tens of workers, and then decided that it needed 1,000. And the blue lines, which I wish the blue lines are showing essentially when the dynamic work rebalancing happened. Right? These are the points in time when we decided to split the work and distribute it further. And you can really see that it's going in stages, right? But the framework is essentially learning what your application is doing in a sense, and like adapting to it, right? Cool. So why does this matter to you? Okay. Well, because it helps the real applications run better, I hope. So we will look at one of the a case study. There's this application that one of our sister teams in Cloud ML cares about a lot. So we are monitoring what that application is doing, and it's a standard ML preprocessing pipeline. It's applicable to pretty much any ETL. You take a data in some format and you create it. You convert it into format you want, right? So this particular application takes the data in tab-separated value format and converts it into TensorFlow record format. And input data are click-through logs from Criteo. I think it's a public data set. And the pipeline is reasonably straightforward. This is our pipeline graph from Dataflow UI. So we have a stage that reads from text. Then we decode it. And then we have this meat stage called analyze and transform. And then we encode the output, and we write it. And we make a small side output with some metadata there, just like store some information about the run. Okay. This is a preprocessing step that can apply to many, many users. And those users will differ on input sizes and the content of the files. And they will also differ on analysis parameters they want to do. Right? Like this analyze and transfer step is a meat of transformation, right? And it has some things like, what is the threshold for merging the things? How big, output files you want, or things like that, right? And users may want to configure the application differently. These are not tuning parameters. These are application parameters that affect what the output is, okay? So how would you tune application to run the best it can, given that the users can set all of these different things? It's a trick question. You don't have to. You're using Dataflow. OK, so a bit more of context. So machine learning workflows for sparse data typically have 3 steps. You preprocess data, you train, and you serve the model. And in this case, we are looking only at click-through rate prediction. But if you wanted to do things like recommendation, you would have a different input types that you would want to add, things like the inventory or user information, right? And you would have to perform join, which would make it much more complicated pipeline than the one that we are looking in this example. Yeah. And for more details, you can see many of the next ML sessions. And actually, the code of application is a Python SDK, Beam Python, and it's available in GitHub. OK, again, reflection on the pipeline, read, decode, analyze and transform, encode and write. Right? So running this pipeline, let's look how it looks like. So we have a 10 GB input. It's a fraction of a data set. And this is how the worker profile looks for this pipeline. So on the x-axis, we have time. This is run from a week ago or something. On the y-axis, we have number of workers. And as the pipeline starts, our initial estimated that it should have around 40 workers for reading. And then the blue line actually shows the workers, actual workers. The green line is our estimate and what we want, what the system is asking to happen. So the blue line ramps up to 40. And then it runs, and it figures that I can use a little bit more parallelism here. So it jumps up, and then once it gets to a bigger stage, like analyze transform thing, it jumps up a lot, and it goes from around 50 workers to 107 or 8. And then it finishes, and it's done. So this job was around 21 minutes, 20 seconds, and it used 38 CPU hours and 144 gigabytes of RAM and 5 terabytes of PD hours. Now, the same input, but with a different threshold parameters for the pipeline. So this is application parameter. Like I wanted to produce more detailed results. So it makes it more expensive to run it, or more computationally expensive. So this is how that one looks like. It looks similar, right? But the differences are the y-axis now goes to 150 and above. Okay? And again, we start with a maybe slightly higher estimate. We keep going. There is, again, that bump when we figure out there might be some more parallelism here. Let me utilize it. And then once we get to the expensive stage, like we just, ramp up high and then like add some more, and we run it at like 173 workers. And the runtime is almost the same, 22 minutes, 17 seconds. But you end up using way more resources, 61 CPU hours, 230 gigabytes of RAM, and 8 terabytes of PD. My point here is not that this was more, computationally intensive. My point is that it was the same command line as far as Dataflow is concerned. The only change was in parameters. And we were able to keep all these workers busy for the duration of the pipeline. Right? They were utilized at 100% in terms of what they are doing. Right? So now we want to look at the larger scale. The full input size is 1 terabyte. What does that do to the graph? There are a few changes. First, our y-axis goes to 1,000. This is a system limit, and I'm going to show it later. And when we initially started, we figured out around between 500 and 600 workers would be good. So we again start running the first part. We had a bump, we think there is more parallelism here, but then we were like, no, we were good. So we came back down. And then we have this part, which actually corresponds to a group by key step. What happens in a group by key step is you collect all the data from incoming shards, right? And then you have to group them by key, right? And this operation is sort of two-step one, and you cannot proceed the next stage until you're fully done, because you need to be sure that you saw all the keys. So what happened here is that the group by key couldn't really fully keep up with what was coming in, so it had to finish. Now, they do use dynamic work rebalancing, but there are always more opportunities for improving, and this is one of them. So what happened here is, while we were finishing the tasks that weren't parallelizable further, we shut down the other ones. There was no reason for these machines to sit there idle, because they couldn't do anything. Okay? And then, once that step was done, we shoot up in parallelism, and we were using the system-imposed maximum. We do not go above 1,000 workers unless you tell us. We think it's a reasonable maximum to have by default. OK, so this job took 1 hour, 33 minutes, and used quite a bit of resources. And in terms of scalability, the input ratio size was 100 times. The CPU ratio size was 104 times. In terms of gigabyte RAMs used, it was 104 times as well. And the PD usage was 52 times X. And the wall time ratio was 4.2. Right? The ideal scalability in this case would be 1, right? But Amdahl laws is pretty strong. So this part where we had to shut down and slow down really does affect the performance, right? But we don't waste resources. OK, now let's look at the performance of this application over the last 6 months. Again, it's an important application to the sister team, and we are with them monitoring what's happening. So the red line shows the runtime over a 6 months period. Okay? The initial drop there was the bunch of data flow level improvements that we did on the Python SDK, or Beam Python SDK, after GA launch. So we spent time improving the connectors and these things, and that had a very visible impact on the runtime of the performance. Note that the application did not change in this time period. So these are all the improvements that are happening, or all the changes were happening from system perspective, from tool perspective, right? On this here, we enabled the auto-scaling, and that was another drop in duration time. And then at this time, someone had a brilliant idea that, hey, we are looking at the resource usage in this. What does it mean for the cost? Okay? So we start tracking how much the application costs at that point. And I think in that moment, we were running at 62 minutes wall time, and it cost around $225. And end of January, we are at 57 minutes, so there were no major reduction in the wall time, but our price is significantly lower. And what this tells you is that the system became more efficient. You're not, maybe your wall time is that much, but you are using less resources. And it's the same application. They're running it continually, essentially, right? And I think this is like one of the core things that I would like you to come out with this, is like we really care about the cost-effective performance, and we treat it as a first-class feature of the system. Okay? And with that, we'll switch gears and look at our Cloud Dataproc product. We will look at how the system-level improvements affect the performance in Cloud Dataproc. Okay? So what is Cloud Dataproc? Dataproc brings the widely used Apache Hadoop and Apache Spark ecosystems to GCP. It is fully managed, it's easy to use, it's fast, and it's cost-effective. And I'll talk about all of them. So how does the Cloud Dataproc cluster lifecycle looks like? Well, when you need to, you start one cluster, you then use it, and you run Spark, Hadoop, Hive, any of these Apache open source ecosystem tools. And then when you're done, you shut it down. You delete the cluster, so it doesn't use your time. While you're using it, you can still modify the cluster. So you start with a cluster with like 20 machines, whatever. Now you need 50. And you can pretty simply change that to a bigger size or smaller size, depending what you need. So this sounds, this is exciting. I mean, if you think you bring up your cluster, you use it, you shut it down, there is some power to it when you do it. And but like often Spark and Hadoop ecosystems are slow to deploy, and they're costly and complex. So start, use, and delete sounds wasteful if you're going to spend a lot of time starting the things. But that's not the case with the Dataproc, right? Oh, yeah, and we do 1-minute billing. So starting a Cloud Dataproc is as simple, literally, as going to a web page, clicking Create Cluster, optionally configuring it, and doing Start. And within 90 seconds from the beginning, you can have machines spin up like fully configured. Whenever you need to change it, you go back to configuration page and you change the parameters that you want. Okay? So the major goal of Dataproc is to bring the power of Google Cloud Platform to Spark and Hadoop users. The team builds connectors and integrations with other cloud products like BigQuery, Cloud Storage, Cloud Bigtable, Cloud Spanner, Compute Engine, and allows you to read and write from these seamlessly. One of the example jobs that they have is like PySpark job that takes the data from GCS, uses a PySpark, and then produce the output in a BigQuery. Okay. So how does it look like under the hood? So we have our clients on the left-hand side and the Google Cloud Platform on the right. And Dataproc exposes the REST APIs for managing the cluster, for managing the jobs, and other operations that you may want to do. So you can access these APIs through UI, or you can script against them, right? Like you can program against this API. Next, Cloud Dataproc has the clusters that they'll build on top of compute engines. And there is like this Dataproc agent that manages. It's sort of a control plane, and it manages your cluster. Make sure that VMs are up and things like that, right? And this also, the image that we have is built on top of BigTop. So it comes with the Spark, Hadoop, Hive, and many others things that are there. When the cluster is brought up, we also bring up some persistent disks, and we install the HDFS on them. Okay? Or we make them available through HDFS. However, if you want to use the start, use, stop cycle, you cannot really keep the input and outputs on the HDFS because it goes away when you're done. So what you do instead is you put your inputs and outputs on Cloud Storage, in BigQuery, on one of these services that are always up, but not like but do not come down and up with your cluster. Okay, so at some point on a break day last year, in our regular performance analysis things, we noticed a problem. And the problem was that for the jobs accessing a big amount of data on GCS, the read and write were spending a lot of time in SSL-related code. So much more that it wasn't bottlenecked on network, but was bottlenecked on CPU operations, right? Like we're bottlenecked on CPU. Remember, I said like that we recommend GCS to our users, so this was surprising. So we analyzed it and determined that Java-based SSL implementation is very CPU-bound. Okay, and once we identified the problem, we could come up with a 50 solution momentarily that would help the people who are affected make it run better, but we really wanted to do it in a systematic way to make it available to all of our users. And that meant that we needed a system-level solution, okay, that will be deployed to everyone and will make everyone's life better, not just a few that that were complaining that things are slow. So what's the solution? The solution was to switch implementation to boring SSL. And because it's a boring SSL, his boring name, I had to have a unicorn that sparkle. So what it involved, well, quite a bit of things. But essentially what we will, over the next few weeks, the old Dataproc customers will have significantly improved read and write performance to GCS. And essentially, these are the results. So we're looking at a test DFSIO benchmark. X-axis is throughput. The more the merrier, so you want a higher throughput. And light blue is the old method, and dark blue is the boring SSL method, right? And essentially, we are seeing 2.5 times faster reads and around 20% faster writes. And there are no user changes. It's just like the new system configuration that runs. And the different jobs will see different benefits, because if your job wasn't bottleneck on this is not going to significantly improve it, right? Because your end time depends on more than just this. But this is another example of systematic improvement that goes in a system, and if you were watching your application over time, will make it cheaper and more efficient to run. Okay. Okay. So we'll have some takeaways now. So when trying to achieve the performance, and you want to do that automatically for your data processing applications, the tools have to look at the different types of factors, right? We had application-level factors, environmental factors, and system factors. We try to systematically address all three of them across both of these products and across those GCP, right? Performance is something we care about and we look at all the time. We have dedicated people for that, right? In our talk, we covered the application aspects and the environment aspects and how we deal with them through Dataflow, looking at the dynamic work rebalancing, auto-scaling, the graph optimizations we do. And on the system side, we looked at Dataproc and how they improved one of the core system libraries by replacing it, essentially, to bring the performance, to increase the performance of read and writes to GCS, which is a very common pattern that our users use. So data processing tools help your application achieve performance automatically. We systematically tackle different factors that affect the performance. And we provide real-time auto-tuning in Cloud Dataflow and system-level improvements in Cloud Dataproc. And improvements made to the systems and we make improvements to the system and tools continually. So we take the performance available to you out of the box, and no knobs are needed. Okay.